Okay, I didn't expect anybody would have any real trouble with this question, but I wanted to make sure, and I'm right. Okay? And your restriction here is that the denominator can't be zero. Numerator can be anything at all. Okay? And no matter what X and Y are, your numerator is a perfectly good number. Okay? And so is your denominator, but sometimes that number is zero. Okay, so denominator can't be zero. Well, so let's just write out all the steps. Because you do want to get in the habit of writing out all the steps. Sometimes it's not as obvious as it is here. Denominator is not equal to zero, so x plus y is zero, so x is equal to negative y is forbidden. That's not in the domain. So the domain could be written as the set of points x, y, such that x plus y is not equal to zero. Okay? And what's that look like in the xy plane? X equals negative y. Is this line, right? So this function's not defined on that line. Okay. What's the limit of f of xy as xy, point xy approaches the point 2, 1? Think about it for a minute. Tell me if you think you know. Because I lost half a night's sleep last night, but I feel great. But I'm okay. Okay. Um, and my brain's working well because it's not trying to work too hard. And that's too much for me. Okay. What I said was a limit f of xy as xy goes to 2, 1. What is it? Now, I think I probably posed that and then paused and didn't turn the recorder back on. Well, the limit is 2/3. And what I said was if xy is in a small enough neighborhood of 2, 1, so here's 2, 1, and this little circle, everything inside that circle is a neighborhood of 2, 1. Okay? If that neighborhood is small enough, then I can make f of xy as close as I want to 2/3 just by making the neighborhood small enough, right? It's a lot like an epsilon. It is sort of an epsilon delta thing. We're not going to get too deep into epsilons and deltas because, again, the weather disaster that started the semester is still biting us and will continue to throughout the whole term. Okay. So there might be some problems that involve epsilons and deltas. Do your best with those. We can talk about them a little bit after you've thought about them. Don't ignore them. Think about them, but don't worry too much. Okay. Probably not going to put a lot of epsilons and deltas on a test. Um, so a more formal statement of what I just said here is if the square root of x minus 2 squared plus y minus 1 squared is less than delta. Now, what does that mean? Well, x minus 2 squared plus y minus 1 squared is the square of the distance between xy n1, 2, isn't it? It's just, your distance formula or just Pythagorean theorem. Okay, so make sure you digest that. If that is made small enough, then we can make this less than any chosen epsilon. Okay? So this is just another way of saying what I said here. If I shrink this neighborhood around 2, 1 enough, I can make f of xy as close as I want to 2/3. And where do I get 2/3? Well, f of 2, 1 equals 2/3. And that's obvious. Everybody got that. If the neighborhood is too big, of course, I run into this line where the function isn't even defined, right? And the point is that, well, this point is separated from the line where the function isn't defined by a finite distance. So I can always make the neighborhood small enough that I can make this statement, okay? Don't want the neighborhood to be too big, but you think of a tiny neighborhood, tiny region. It doesn't have to be a circle, but some tiny region around the point. Okay, now pose the question. If f of xy equals x over y, what's the limit of f of xy as xy goes to 0, 0? Turns out to be a complicated question. Some people say it's going to be 0, but of course, if x is 0 and y is 0, it's undefined. So you're not worried about what happens, though, at the point 0, 0. You are worried about what happens in the neighborhood of the point 0, 0. Well, we need to draw a little picture of something. So here we've got the point 0, 0. Here's the point, and here's a neighborhood. Of 0, 0. Now I'm going to kind of give this one away. There are points in the neighborhood, or there are paths within that neighborhood where that limit is defined, where that limit has a perfectly good value. Let's just say I want to approach this point by a path It's a path approaching 0, 0. You probably can't read that. Here's a path approaching 0, 0. Okay? I've got the wrong path. I did x over y, right? Along that path, x over y would be x over 0, and that's undefined, right? That tells me right away that the limit doesn't exist because there's a path that goes right into that neighborhood and approaches as closely as you want to the origin on which the function is always undefined. So there are points within this neighborhood where f of xy is undefined. If x isn't defined at a point, and no matter how much I shrink that neighborhood, that's still going to be so. Okay? Does that make sense? Oh man, can't get this chalk to write down there. Points for, okay. What I'm saying is for any neighborhood of 0, 0, there exist points where f is undefined. Looks like undefined, so make sure that looks like a U. Okay? Therefore, no limit. Because again, this path goes all the way up to, but not including at 0, 0. Okay? So you can't just say the limit is 0 over 0. 0 over 0 is undefined. Okay, but the limit as you approach might or might not be defined. Okay? Contrast that with the fact it doesn't make any difference in this case, but along a path, I've got to have a color, along the y-axis, everywhere on this path, f of xy equals 0, doesn't it? Because everywhere on the y-axis, x equals 0. So f of x equals x over y equals 0. Now that path doesn't include the origin. You can't include the origin on any path because you're only concerned with what happens in a neighborhood of that point, not at that point. So we can approach 0, 0 along a line where f of xy equals 0. Okay? We can even approach along, let's say, this path, where, let's say, the path is y equals 3x. Looks like it has a slope of about 3, doesn't it? I mean, whatever. Okay, any multiple of x. F of xy equals x over 3x, which is 1/3. Everywhere on this path. Okay, that makes sense? There are all kinds of paths that I can use. Okay? And I can get any value of f of xy I want to in any neighborhood. I wanted xy to, if I wanted value 1/3, I'd use the line y equals 3x. If I want value 14, I'd use y equals x over 14. Okay? Maybe I said that right. You can figure it out. I can even think about, okay, again, let's just do it here. Because this is a point 0, 0. And I could use a path that just spirals in and keeps spiraling in, but never gets to 0, 0. Okay? Along this path, there are always points on the x-axis where the thing is undefined. And there are also always, I'm sorry, where the function is undefined. Okay? This isn't our xy over x plus y function. I almost got that confused, so watch me. All right? because this function is undefined everywhere on the x-axis, and that's the only place. But there are always points. I mean, there are all these points on this path where the function is not defined. Any point on the x-axis. If there are paths where the function is undefined, then the limit doesn't exist. Furthermore, this is a little bit vague, but where f of xy always takes different, I better say constant, probably can't read that, but different constant values. And the limit is not defined. Now, I mean two paths approaching the point at which you want to take the limit, okay? So digest that idea, because that's one of the tougher ideas you have in the first section. I'm going to be assigning the first two sections of chapter 14, okay? So think about that for a minute. I just want to be sure I stay on track. Okay, so we've touched on the ideas of domain and range. The domain of that x, y over x plus y function cannot include anything on the line y equals negative x, okay? So the domain is restricted because of the denominator not being, because of the restriction that the denominator cannot be zero, okay? You also have things like the square root. Whatever's inside the square root has to be non-negative, right? So you know about that. You've known about that since pre-calculus. You have to review it. But the same thing applies to functions of two or more variables. Just a little comment. If f of xy is square root of x plus y minus 5 over 3x minus 6y, x plus y minus 5 has to be greater than or equal to 0, right? Because it's under the radical. So y has to be greater than or equal to 5 minus x. Well, your graph of y equals 5 minus x is just a straight line through 0, 5 and slope of negative 1. And y has to be greater than 5 minus x. Here's where y equals 5 minus x. So above the line y equals 5 minus x is okay. Does that make sense? If not, digest it. Okay? Think about it. But if the square root of something is in the definition, then that something has to be non-negative, has to be greater than or equal to 0. And you just solve this inequality for y, and you take the line where y equals 5 minus x, which looks like that, and you can work that out if it's not obvious. And then y has to be greater than that, okay? So you might have to think about that a little bit. The other thing is, 3x minus 6y can't be 0. So y can't be equal to x over 2. So where's the graph of y equals x over 2? Let me circle this in a different color and come over to the graph. Here's the line y equals x over 2. Okay. Now this is not, the x and y scales are different, but this part of the line that's in the part of the xy plane that would be okay for the square root has to be excluded. So this part of the line is not okay. So everything above the y equals 5 minus x line, except for the points on the line where y equals x over 2, are in the domain. That makes sense? So it's just the same restrictions that I just went over in pre-calculus class. Okay? Should have gone over 2 or 3 weeks ago, but with the weather, some other factors. It's just domain and range. And the main restrictions you got to worry about are you can't take an even root, square root, fourth root, sixth root of a negative number. And you can't divide by 0. There are other restrictions with sines and cosines and tangents and arctangents and all that stuff. Okay? No real restrictions with sines and cosines when you get into the other functions yet. But you're probably not going to encounter those at this point of the course. All right. So that's the idea of domain and range. Let me take a quick look since I've now got it right here. Okay, level curves. I want to talk about level curves. Now, have you encountered that terminology with quadratic surfaces? We've done it, but you might not have encountered the terminology, so let's make sure we understand what that means. Let's just stick with simple function. Let's go back to the function we started with. Now, I haven't thought this through, so I might be getting myself in trouble. I think I'm going to be okay, and if not, we'll change the function. I haven't thought it through because I know if I plan something, something's going to come up, and I realize that you don't understand something that would go along with the plan. So I know where I'm going, but I improvise it as I go. So I'm improvising this thing without having thought it through. Okay? So I'm on dangerous territory, but that's all right. You get there in mathematics. You might as well see it, and I'll show you plenty of it. Okay. So you got this. Now, the level curve f of xy equals 4. That's a set of all points in the plane where the graph of the function is 4 units above the x-axis or the xy plane. Okay? So we could say z equals f of xy equals 4. Now, what's that? I'm probably going to hate myself for having done this. Xy over x plus y equals 4. So that xy equals 4x plus 4y. Solve for y. Then you get y equals, well, let's see, you bring this 4y over here and you get xy minus 4y, which is x minus 4 times y. So y equals 4x over x minus 4, I think. Okay? Let's pretend that that's actually a solution. Well, let's multiply it back. We get xy minus 4y equals 4x, and we subtract the 4y. Yeah, that works. I'm pretty sure that's the right solution. I don't want to go through the steps. You can solve it. Okay? I've told you, because this is something that it's a little subtle. You got a y here, a y here. You got to bring them all over here and then hope that you can factor y out. Sometimes you can't. And then you're stuck with an implicit function. Okay? And you're not going to be able to graph it easily, but this is easy to graph. Okay, that's just a rational function with a vertical asymptote at x equals 4. And it takes value 0 when x equals 0, so I know it goes through this point. I know its limit as x approaches negative infinity is 4. So I suspect that the graph is going to look something like this. And of course, as x goes to infinity, it's also 4. So there's your graph of this function. Now that goes back to pre-calculus. You probably haven't thought about a rational function since you took pre-calculus. It was even covered in your pre-calculus class, which it really has to be, but isn't always. Okay? That's a very simple rational function. You might want to review rational functions instead of just punching this thing into your calculator and accepting the graph that you see. Okay? Yeah, if you punch it into your calculator, put it into a computer algebra system, get it to graph, I think it's going to look something like that. But I did that kind of quickly. Remember, I'm functioning at half a night's sleep, so who knows what I might have done. Okay? But I think that's right. Um, and the other thing you want to look at is if x is between 0 and 4, x minus 4 is negative and 4x is positive, so that the graph will be in the negatives. Okay? Then to the left of that, x is less than 0 and x minus 4 is still less than 0, so you get a positive. All right? Those are the things you want to think about and look at, because anything could pop up. I don't know, you're going to run into a rational function on your homework. I haven't looked specifically at the problems, but at the whole idea behind them. And that is how you get a level curve. This means that if you graph this function, you can draw this level curve. Let's be careful. The asymptote is at the line x equals 4. So here's the line x equals 4. Thing will go through the origin. It's going to be negative on that side and positive on this side. So it's going to come down like this and be asymptotic here, if I'm doing this right. And then for larger values of x, it starts way up and comes down and approaches this thing. So, okay, right there is the same function in the xy plane. And then if we draw the graph, just raise every one of these points 4 units. And we get this curve up here. And down here, we raise every point 4 units. And that's implicitly in the y direction. So if we raise this 0.4 units, we get this. So we get something that looks like this. And this curve is directly above this thing, which is really this thing looked at from a different perspective. And over here, same thing. So right here is part of your graph of the function, the three-dimensional graph of the function f of xy equals xy over x plus y. That's a level curve. Okay? We could also now label this thing as z equals 4 curve. Now, what if we want z equals 5 curve? It would be 5x over x minus 5. You can do the solution, but it's just similar to this. It's just we're going to have 5s where we had 4s, I think. Okay? So what's that going to look like? Well, we'll contrast it by saying, okay, now here's the line x equals 5. That's going to be our vertical asymptote. And y equals 5. Well, it's going to be a little bit above y equals 4. And now we sketch z equals 5 graph, being somewhat careful. We've got to come down. Looking like we've got to come down through here and still be asymptotic to this, but that means these curves are going to cross, and I am suspicious of that. I don't see anything wrong with what I've done, though. And since I never make mistakes, there can't be anything wrong. Okay. Uh, uh, so I'm not going to go on with this because if I draw it, it's going to confuse me, and that'll probably confuse you. Okay. Typically, what you would get if you've got like an elliptic paraboloid, okay? You can visualize an elliptic, even just any paraboloid that opens up along the z-axis, right? Your level curves are just going to be, if it's just a circular paraboloid, your level curves are just going to be a series of circles centered at the origin, okay? If f of xy equals x squared plus y squared, that's z, equals f of xy equals x squared plus y squared. It's a quadratic surface. You know that the cross sections are parabolas and they're all symmetric. So you have a paraboloid of revolution. Okay? If this is the z equals 1 curve, and I'm just going to put 1 here because I don't have room to write z equals 1, but that indicates that this curve is the part of the curve where z equals 1. Now let's just look at a parabola. Not a particularly well-drawn parabola. Here's z, and here's x or y or any line in the xy plane that goes through the origin. Okay, so we'll just call this x. And here's z equals 1. Well, that occurs for x equals 1. Z equals x squared if we're in the xz plane, because y would equal 0. So it's just a z equals x squared. There's z equals 1. Now, if we come out to x equals 2, we get z equals 4. So this would be the level curve I'm writing it really small. This is a level curve where z equals 4. I'll go ahead and write z equals 1 here, but it's going to be illegible. And z equals 9, where the radii of these curves are 1, 2, and 3. So radius here is 3, radius here is 2, and so forth. Does that halfway make sense? If you rotate this curve around the z-axis, you get this paraboloid. If you take the part in the xz plane where x equals 1, you're going to get z equals 1. So if you then rotate this thing around the z-axis, this point will make a circle of radius 1, and there it is. It's a topographical map, okay? Your contours are going up. So if you go from x equals 1, which would rotate to give you this circle, to x equals 2, which rotates to give you the circle of radius 2, the height of the parabola above these circles in the xy plane goes from 1 to 4. Just like here on the parabola in the xz plane, if you go from x equals 1 to x equals 2, you go from z equals 1 to z equals 4. And then if you go out to x equals 3, you're going to go all the way up to z equals 9, right? So if you understand what a topographical map looks like, and you might or might not have encountered topographical maps, that's what you've got. Your book will give you additional examples, okay? If the numbers here, instead of z equals 1, z equals 4, and z equals 9, were reversed, so you got 9, 4, 1, then these circles would show you a parabola that's decreasing. It's opening downward. Ponder that if you need to. And, read the book, look up topographical maps, look up contour lines. Your book is going to explain it quite well, okay? There's an example. Let me pause for a second. Oh, no, I don't want to stop recording. Come on. Now, this gets pretty neat. You've got functions of 2 variables, and you can do level curves, okay? But let's say you got a function of 3 variables. And let's just use a function that you can handle. F of xy equals x squared over 9 plus y squared over 16 plus z squared over 25, okay? If f of x, y, z equals 1, then what equation do we get? Write out the equation. Just keep yourself engaged and active, although everybody looks pretty engaged and active. Just make sure you're not faking it. Okay. And if I have any sense at all in interpreting people, nobody's faking it. Okay, remember to turn the recorder on a little bit late. But if f of x, y, z equals 1, and f of x, y, z equals x squared over 9 plus y squared over 16 plus z squared over 25, then x squared over 9 plus y squared over 16 plus z squared over 25 equals 1, right? Just substituting equals for equals. So No, somebody, at least one person. That's an ellipsoid, which is pretty easy to visualize. Okay, just take a sphere centered at the origin and stretch it out by factor of 3 in the x direction, factor of 4 in the y direction, and factor of 5 in the z direction. And you got kind of a blunt football with inconvenient dimensions. Okay, would be real good to use that in a football game. Although, if you're desperate, you can still use it. Be hard to catch and hard to throw. If you're used to a football, you have to adapt. Okay. Okay, so this is a level surface. For z equals 1. Okay. What if z equals 4? Well, no, level surface for it's not z equals because it's f of x, y, z equals. Well, it's x squared over 9 plus y squared over 16 plus z squared over 25 equals 4. So what's that surface look like? Well, you want a 1 over here. So you divide both sides by 4, you get x squared over 36 plus y squared over 64 plus z squared over 100 equals 1. And if you remember how to do ellipsoids, which are probably the easiest, except for spheres, the easiest quadric surfaces to understand, you see you got x squared over 6 squared, y squared over 8 squared, z squared over 10 squared. So your semi-axes in the x direction, you got to stretch it out by a factor of 6. In the y direction, you stretch it out by a factor of 8, square root of 64. And in the z direction by a factor of 10. So it's just an ellipse with twice the dimensions of this one. Okay? So you might need to process that. This one has double the dimensions of this one. Still an ellipsoid. And as you keep increasing the value of your constant, okay? Because this is the surface on which f of x, y, z takes a constant value of 4. This is the surface where f of x, y, z takes a constant value of 1. If you increase the constant value, you're just getting bigger and bigger ellipsoids. If this is a temperature function, then the temperature is 1 degree here, it's 4 degrees here. So you're on this smaller ellipsoid, temperature is 1 degree. You go to bigger ellipsoid, temperature is 4 degrees. Okay? You go to a bigger one, whatever value, and your temperature is increasing as you move away from the origin, but it's increasing faster in the x direction than it is in the z direction. Because by the time you get out to x equals 6, your temperature is the same as if you have to go up to z equals 5, to z equals 10. Okay? In other words, the ellipsoid is shorter in the x direction than it is in the z direction. Okay. So you get a quicker temperature change if you move in the X direction than if you move in the Z direction. Something you can visualize. Okay. So I could ask if the temperature is 1 degree, where do you move most quickly and most quickly get up to a temperature of 75 degrees where you feel really pretty good. Okay? Makes sense? Think about it. Okay. Okay, now what I went over last time was about partial derivatives. Okay? We did pictures. We talked about several aspects of the thing, but we didn't formalize it or even define what a partial derivative is. Just told you how it relates to the three-dimensional graph of a function of two variables. Okay? And how you calculate, which is pretty simple. If you calculate the partial with respect to x, you treat every other variable as a constant. So that's easy to get used to. And most of the problems don't involve very complicated derivatives. Some of them maybe, because you got to be able to take complicated derivatives. It's just a well-defined rule-based thing for continuous functions. So I'm just going to write out the difference quotient as we get into some notational difficulties if I do what I was starting to do. At a given point, the partial of f with respect to x is a limit as delta x goes to 0 of f of x plus delta xy minus f of xy. Okay? Does that look familiar? That's a difference quotient that you would have seen in pre-calculus and would have used a whole lot at the beginning of your first semester calculus course and probably used at various points, especially in the first semester. Okay? I mean, that's all it is. It's like, okay, here's a graph. And you got your three-dimensional graph of f of xy. You slice it in a plane parallel to the xz plane. In that plane, you've got a curve. We illustrated that last time, so you might want to think back on some of the pictures we drew and think a little bit more in terms of those pictures, and also the pictures you see in your text, pictures you can see if you just type in partial derivatives to the web. Wikipedia will probably give you a pretty good picture. But lots of other sites will, probably a million sites that explain this, okay? And I explained it last time in terms that I tend to use, but it's very similar to what anybody else can do with the pictures, okay? I think. I mean, you never know what somebody else might do. So here is, say, x prime equals x. Now, in three dimensions, what I'm really saying is Here's the line. Y equals C. Above this line, you've got this curve. By X prime, I mean an axis along this line. It's just your temporary x-axis if you're in this plane. Okay? So if you need to digest what I said last time a little more, let's go back. If you look at the AI summary, it gives you a timeline now. Okay? And I've asked it to do a timeline. So it tells you where in the video this is happening or that's happening. And it does a pretty good job of it. Anyhow, so there's some line where X equals C. This is in the Y equals C plane. If we want the partial of the derivative of F with respect to X, we're going to take this point, which is just debating here for a minute. If we're in the Y equals C plane, then Y equals C. So I can say this is F of X and whatever the value of Y is, and we'll call that value C. And it's not going to matter. Okay? So at this point, Z equals F of X, C. And then here we'll let X prime equal X plus delta X. Okay? So that this distance here is delta X. Then at this point, C equals F of X plus delta X, and C, where C is whatever Y happens to be in this plane. Okay? Then on this graph, we have our delta X here. We have our delta Z here. And the slope is delta Z over delta X. And excuse me for crossing two arrows, but sometimes it's unavoidable when you don't plan. Okay. Does that make sense? So whatever your function F is, you just evaluate it at this point and this point, and delta Z equals what? Delta Z is just this minus this. Delta X equals, well, what it equals. Delta X is just delta X. Oh boy. Good thing that that popped up because I would have forgotten all about it. I had a report. Make decisions that affect people's lives. They should run and panic today. Okay. This isn't usually pretty easy and favorable. Uh, but we'll see. Um, okay. So we got delta Z, and that's what I get for not putting myself down for any other committee. I get at least. Okay. We got a delta Z and a delta X. So the slope, which is approximately equal to the partial derivative of f with respect to x, because the partial of f with respect to x is the rate at which f changes as you move in the x direction. Now, the rate that the function changes right at this point, well, the way I've drawn it, the function's concave up, so the actual rate at this point will be a little less than the slope that we calculate with this given delta x, right? But we're going to let delta x approach zero, which brings us down and gives us the equation of the slope of the tangent line, right? And that's something you should really understand from pre-calculus once. I'm not going to belabor it right now when we've only got about 5 minutes left. Okay, so the slope is approximately equal to this. And what's this? I've got this written backwards, so let me rewrite it. Because I was about to, I want to write partial of f with respect to x is approximately equal to delta z over delta x, which is f of x plus delta x c minus f of x c over delta x. And the partial of f, chalk, or my inability to control it, the partial of f with respect to x equals the limit. Then as delta x approaches zero of f of x plus delta x c minus f of x c over delta x. Now c is the same thing as y. C is just a value of y. So in general, right there's your definition, and this is what it means. Okay. Then you can easily, if you understand this, you can easily see that the partial of f with respect to y equals the limit as delta x goes, or delta y goes to zero of what? F of x, y plus delta y, because it's y that's changing now, minus f of x, y over delta y. And you can visualize that by just cutting the thing with a plane parallel to the xz plane, so the yz plane. And I'm not going to draw that. I kind of drew that last time. Okay. But you can do a similar picture. It's going to look, maybe look a similar curve. Maybe it's a different curve. You're going to have a y and a delta y and a change in z due to the change in delta y. Okay. So it's like you got this graph. It's up above it. Okay. And I'm at some point x, y. And I move in the x direction. And that graph either goes a little higher or goes a little lower. Okay. There's also a tangent line right above me in the x direction. And the slope of that tangent line is this partial derivative. If I go that way, then I'm changing y. So I've got to do this. So I change y by a little bit, and I see the graph comes down maybe a little lower toward me. So the delta y is going to be, the delta z is going to be negative. So I'm going to have a negative partial derivative in the y direction. Okay. You might want to digest that. I said a lot of words, so you probably don't want to look at the transcript. You'll never find anything, unless you know where to look. Quick word on continuity. I really want to review the concept. Continuity at x naught, y naught means the limit as xy goes to x naught, y naught of f of xy equals f of x naught, y naught, which simply means as you shrink a neighborhood around x naught, y naught, the value of the function approaches its value at x naught, y naught. Now, again, you might want to ponder that statement, or hopefully at least recognize it when you see it in your textbook, okay? Or in the examples. Well, we're out of time. If you have questions, you can always email me. Unless I go down a black hole like I did last weekend, I'll be checking email pretty regularly. Okay? Went down a black hole with AI trying to get the write a program that it turned out not to be able to write any more than I could. Okay. Difficult test. Okay. Have a good weekend. And I'll get the assignment up there just a little bit later.